All right, let's try the next problem. Just check to see if everything's working before I get going. So hello and welcome. Yep, we're going to take a look at another LeetCode medium. Hopefully this is an interesting problem. Those of you who are interested in it, I suppose. So Reconstruct Itinerary. All right, let's see how it goes. Given a list of airline tickets represented by pairs of departure and arrival airports from to, reconstruct the itinerary in order. All of the tickets belong to a man who departs from JFK, thus the itinerary must begin with JFK. Okay, interesting. So this is like kind of a graph-related algorithm, something like a graph algorithm. If there are multiple valid itineraries, you should return the itinerary that has the smallest lexical order when read as a single string. For example, the itinerary JFK LGA has a smaller lexical order than JFK LGB. All airports are represented by 3 capital letters IATA code. You may assume all tickets form at least one valid itinerary. One must use all the tickets once and only once. Whoa. Whoa. So departure and arrival from to, reconstruct the itinerary in order. Okay, so we have a whole bunch of tickets and we want to basically get from one to the next, something like that. All right, interesting. Excuse me. Excuse me. The itinerary JFK LGA is a smaller lexical order than JFK LGB. If there's multiple valid ones, return the one that is the smallest order when read as a single string. Okay, that's interesting. And we're going to have a vector string, so we have sort of one. So JFK to MUC, and then there's MUC to LHR, and then LHR to SFO, and SFO to SJC. Now I want to see, right, okay, another possible reconstruction. So if there was only one construction, this would be super easy because you can basically have a mapping, a hash map you can create where you have sort of the input and the output, and then you can just walk through your hash map, just kind of reiterate at each one. So you would have JFK would give you MUC, which would then from MUC back into the hash map give you LHR, and you just kind of recurse until, or you would iterate until you've created your full vector. However, you could have multiple solutions, and that could be because JFK you can go to SFO or ATL, and then from SFO you can go to ATL, and ATL to JFK, ATL to SFO. So you could have cycles. So actually this is kind of like a graph problem, sort of. Yeah, because JFK, this is actually a very interesting problem. This ends up being a kind of a graph problem, but it's actually I want to call it a Hamiltonian walk. Hamiltonian. So this went from a very easy problem to a very hard problem very quickly. Hamiltonian path. Okay, you ready for this? Hamiltonian path is a path in an undirected or directed graph that visits each vertex exactly once. It's not a Hamiltonian path, it's actually an Eulerian path, which is a little bit easier than Hamiltonian paths. Eulerian path visits every edge exactly once. However, we can visit the vertices as many times as we want. Eulerian path is a trail in a finite graph that visits every edge exactly once, allowing for revisiting vertices. Similarly, an Eulerian circuit or an Eulerian cycle is an Eulerian trail that starts and ends on the same vertex. So actually what we're looking for is an Eulerian cycle through our nodes, and we want the one with the smallest lexicographical sort at the end. So actually this is not bad at all. I think Eulerian paths are, yeah, there's like properties. It's not necessarily hard to find these. In our case, we actually can assume that one exists, and what we're going to do is we're going to use a hash map, but we're going to, it's going to be interesting how we're going to do this. So watch the chart. Yeah, this shouldn't be too bad. This shouldn't be too bad, actually. Now that we've kind of thought about it a little bit more, I think this is okay. So we're going to have our vector, our strings, and we have, I just like to, oops. Okay. So we don't want to, oh wow, okay. It's a mouthful here. So we have tickets, const vector of, right? Now we're gonna have a return string. I'm gonna build hash map. It's going to be an unordered map of strings to a vector of strings. And I'll explain what we're looking to do here. And we're going to go with, we can actually do a set. I think it's better to do a set. This will give us the lexicographical order on the set. Yeah. Can we return to the same spot twice? If we do that, I think we would want a vector then. We want to maintain the order without having to sort every time. That's a good question, actually. Should we use a multiset here? Yeah, I kind of do want to do that. Like, I think that would be easier. I don't use multiset too often, but I think this might be a good time to try it. Somewhere here is multiset. Not unordered, but ordered multiset. Sorted set of objects of type key. Multiple keys, the closed values are allowed, so please don't use the key pairs. Can we, what does insert do? Elements, oh, can we remove elements? What does this look like? We want upper bound of that range. Inserts value in the position as close as possible. Multiset. So we're actually going to use so we're going to have some logarithmic complexity involved. It's not going to be exactly linear. That's okay. All elements of the key equivalent to key. Can we just remove one? Can we, how would we just remove one of these? Can find the key. All right, so if the count is non-zero, then we could find the key and then remove it. Yeah, or we just, if it's okay. So we can use find with the multimap, I think. So we actually want to use a multimap, which is a little unusual, or multiset rather. I don't use that too often, but I think here is appropriate. So we want basically the graph, or G, we'll just call it G. And we're going to say for auto P in tickets, we're going to say auto S1 or air1 or A1. We do just A and B, tickets of 0 and B is tickets of 1. Right, we know this is how they're set up. And we're going to say G of A dot insert, or G of A dot, how do we do that now? It's actually the G dot. G, yes, G of A is a multiset, which we insert B. And G of, and that's it actually, it's G of A to B, that's all. Right? And then now, build build return string, return array. Yeah, we don't have to comment this. I think it's clear enough what we're going to do. So we're going to say for, how do we do this? Oh, yeah. Okay, I know what to do. So really it's a while loop. And we want to say int n equals tickets dot size while n minus minus string which starts off at this at JFK, right? So JFK, and we're going to say oh, what do we, hold on, this is, I think we want a multimap of string to strings. I think that's what, I don't think we want an unordered map. I think we want actually a multimap. It's so confusing. No, it's a multi-set. It's really confusing. It's really confusing. There could be, yes, it's a multi-set. All right, we gotta get that right. So just take the first of the multi-set. That's really all you need. So we just say auto it equals, or just first equal, or yeah, auto it equals, it's going to be G of which dot begin. And we'll say if it is not equal to G of which dot end, and we say if G dot count of which, then we do the following, which should always be true, basically. Like, we don't actually need to check that. Else will break, I guess, I suppose. So this should exist, right? And we're going to say it equals G of which begin, and if it's not equal to, if it's equal to end, then also we would break. Otherwise, so things that basically shouldn't happen. Standard string S reference S is going to be G of it, really, of it. And then we're going to which equals it, right? Let's do which equals it. And then we're going to say ret dot push back which. Same thing here. And then we're going to, that's it actually. Oh no, we're going to remove G of which, oh no, excuse me. Yeah, I'm sorry. Let's try this again. Standard string reference S equals this iterator, push back S. I'm going to remove the iterator, so G of which dot begin, not begin, but just G of which dot erase, really is what it is. Erase iterator, and then set which equal to S. There you go, that's what I want to do. want to push back this value and then delete this and then update. Right. A little confusing. And then turn red. Now, does this compile? Let's start with that. Compiler error. No visible overloaded operator, unordered map. Oh, okay. Oh, okay, fine. We'll do. I guess that's interesting. What is? Why is this? Oh, that's why. I'm sorry. That's my mistake. It should be auto. This is P, not tickets. That's my mistake altogether. Const qualifier. Can I do this? Const. Runtime error. Nice. Nice. What's the runtime error? What? How does that happen? Where does that happen? What is going on? Got two of these. We don't need both of these yet, but what? Why would we get a runtime error? Oh, okay. Why would we get a runtime error here? That should not be an issue at all. Okay, so. Excuse me, well, I guess we'll find out. We're just going to print a bunch of things. Try to find out where this is happening, where we're getting a runtime error in the first place. I thought I was pretty careful about where. Okay, to test one. Pretty careful about where this is happening. You know what, where. Two. Test three. Pretty careful about not, I guess, accessing things that don't exist. 1, 2, 3. Okay, and what about 4 maybe? Okay, so is this the one? We don't get to 4. What about 4, 6, and 5? It looks like this is the one that's causing issues. Oh, we get all the way to 5. Actually, this is the one that's causing problems. Maybe this isn't supposed to be a reference. Okay, that seems to be the problem. Yeah, I think. Yeah, being a reference, I think, causes problems here. You may need to copy. Yeah, it's probably better just to do it this way, without it being a const reference. I was correct too, by the way, which is what we thought it would be. Oh, didn't mean to open that. Okay, let's see how we do here. Oh man, what's going on with my armpits? Sweet. Let's see if we can get a more complicated test case going here. I don't know, that's gonna take me a while. Let's just go for it. Well, let me just, hold on. Let me just see, all right, if we have empty, if we have one ticket, JFK, MUC, if we have 2 tickets, let me just be a little more careful here. I don't know, ABC. Really doesn't matter. Just be a little more careful. It's not just immediately. Okay, runtime error, nice. Not exactly what I was expecting. Pretty interesting. So, is this the one that we get a runtime error on? No, that's fine. Oh, really? One of these other ones we get a runtime error on, huh? That's fine. What about this one? Really? We got the one with two... No kidding. Runtime error. Oh, it's just... Oh, that's why. It has nothing to do with the code. It's the test case itself. Okay. Well, I'm tempted to just kind of go for it, you know. Whoa, oh, that's why. I know why. The error is still there. That's my mistake. What about like an invalid test case? What happens if we do that? Do like JFK, ABC, and these two. How about this one? What do we do if we with this? A bad test case. What happens? What do we expect? Wrong answer. Output JFK, ABC. Oh, whoa. Really? MUC. No. Interesting. All tickets form at least one valid itinerary. Interesting. Is this supposed to do this? JFK and MUC, MUC to J. Does it go back and forth? It goes to MUC and it goes to ABC. I mean, is this really wrong though? Right? If you don't actually have a valid itinerary? I don't know. I'm kind of afraid. Like, this doesn't seem to match. I don't want to code it up so that way it gets this exactly. Like, what if we do MUC, ABC, and then another one? Like, shouldn't we get like an invalid test case or something? ABC, CDE, right? Like something like this. MUC, CDE, ABC. I don't get it. Let's go for it. Let's see what we get. Wrong answer. Oof. Oof. Ouch. Ouch. I don't know. I was a little confused, but actually I thought that my code does handle this case. KUL, and then enter. Oh, I see. Oh, I see the problem. There may not actually be a path if you go that way. Ooh. I didn't even think of that. Uh-oh. So it looks like we do need to do a graph search. Oh no. That's so much more involved. No. Uh-oh. No. I didn't really think about this too much. Yeah, this looks like we do need to do a kind of graph search. However, I didn't think about that. That even though you had multiple choices, it's not necessarily the case that that every possible choice will give you a graph that you can traverse. Oh no. Oh no. No. This is very awkward. Uh-oh. Oh no. Not only do we need every Eulerian, not only do we need to get an Eulerian path, we also need to ensure that that path is the lexicographically smallest path. Well, I guess we could do a graph search for Eulerian paths, and then each time you find a path, you do a depth first search, and each time you find a path, you update. Do we go through every possible path, though? I mean, that's a lot of paths, right? It's probably so much harder than I thought it was going to be. Just like traveling salesman problem. No, I don't think so. There's a lot of possible paths, right? Oh, no. 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 Oh. Let me go lay down for a minute. This is almost depressing to think about this problem, this question. Oh. I got wrecked. I got owned. I was just hoping it was going to be that easy. Oh. I didn't really think too long or too hard about it. No, it's definitely not that easy. Yeah, if you're dealing with Eulerian Eulerian paths, then you best not jump the gun, jump too quickly into the solution. It's probably a little more complicated than you realize. A little slower. So, all right then. What's the problem? What's the issue? How do we even solve this? Well, there's a good number of edges possibly, but I mean we can create the, what do they call that? There could actually be, right, like I said, there could be tickets back to the same airport multiple times, I suppose. That's why I wanted to use a multi-set. Same departure. You can basically go in circles a few times. I wonder if that's part of the, I don't know. I don't know. I didn't think about that. So you may not need a set anymore then. Maybe just a vector is fine. And, oh man. Oh no. Oh no. How do you even do this now? Oh, excuse me. I don't do work with too many algorithms that could have a multigraph. A multigraph is a graph that could have, between vertices that could have multiple edges, or an edge represented multiple times. I think the algorithm that we end up using could use a multigraph. However, it seems unlikely that there even would be a multigraph for this, that there would even be. Basically, you have the same ticket multiple times. I don't know. It doesn't say there that you couldn't have that. Oh, no, man. Excuse me. Oh, boy. This is questionable. Doesn't really say if it's directed or undirected. I mean, it's kind of directed, the from and the to, somewhat directed. Man. You don't really need a multi-set anymore. Definitely not. Just a vector should be fine. Then, well, yeah, I mean, I think just a depth first search algorithm is what you're going to want to use. And pretty much the state is, yeah, so I think a depth first search is the way to go. And what you're going to want to do is basically the state is going to be, you're actually going to modify the graph itself at each step. Excuse me. Yeah. Yeah, you're going to access the adjacency graph. You're going to modify the graph at each step. And when you have, you're going to have a count also, I think you'll keep track of, which just counts how many edges, how many tickets you've used, how many edges you've gone through. And once you've, I suppose you'd also have a really just a vector, a return vector that you'd be working with, and you just append to the back of that vector the next hop site. Once you've hit the number of tickets, so the size of that vector is the total number of tickets that you're using, then you return. Otherwise, you just pass right through. You just don't iterate anymore. So these dead paths just kind of die off. Yeah, I think it's simple depth first search should work. And then each time you just, I suppose you would push into the return vectors. I suppose you would compare also the final return vector against the return vector that you're considering, and keep the lexicographically smallest final return vector. You might want to use a comparison lambda. I don't think you really even need to. I think you could just do, yeah, you could just compare the vectors directly. I think it'll work for strings because strings have comparators between them. We'll do an index, but element by element comparison. I think it does that automatically. Yeah, I mean, yeah, I guess it's that simple. All right, maybe this is my own fault. Maybe I didn't. Yeah, maybe I'm just I was too hasty. I should have considered this to be a graph problem and gone for the graph solution first, because it's not too hard. The depth first search, the graph search, the backtracking algorithm. I don't know what it'll look like, but man, I was hoping this was gonna be so much easier. I goofed. So just build map or build graph. You're actually going to be modifying the graph as you go, which is kind of interesting. So vector of strings, G. Oh, wait, let me go back. Graph, vector, return, vector, set current, oh. Vector string G, B tickets, G of A, insert B, or just push back. So that gives you your neighbor set, and you don't really need to do these things. Well, yeah, the ticket size you still want for N. Let's do this. Got our DFS. And a DFS, and we're going to use 1 ticket initially. All right, we say ret or current dot pushback JFK, and DFS with a 1, and const. So we have a few things. Int num tickets const Oh, how many tickets do we have? 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4, 5. Or num stops, we'll say. Yeah. So we have to do num stops is going to be equal to the number of the tickets n, or num stops, yeah, as n plus 1. Const string which stop. And then finally, want auto f for our recursion. And we're going to say if num stops is equal to n plus 1, then we're going to return consider current. We have compare current with ret. And we're going to say for auto n in G of which stop. Going to go ahead and now here's the tricky thing. We actually want to modify G itself, which is kind of confusing. So yeah, we can do something like this. We can say standard vector int temp or string temp is going to be copy or just copy constructor G which stop. Yeah, we want to use we want to copy this. That's not really how this copy command works. The reason why I want to copy this is we want to actually modify this as we're going. And because the next time you visit this vertex, you actually don't want to have this value available. The thing that's confusing is that you're looping over all of these values. So it's, I think you do need to copy the portion that you're looping over. That way when you return on the stack, or no, or you're just not, well, you know what? I think it's okay because you're sort of, it's weird. I don't know if we can do it. We could try it. I don't know. Looping over something that you're modifying can always be kind of confusing, but the way that we're doing this now, it actually might be okay, even though it's a little weird. So you would actually say G which stop dot pop back, or yeah, you could erase really. Kind of want to set them if you do it this way. Yeah, multiset. And then you would want something like yeah, no, then it gets really awkward too if you're deleting iterators. Super awkward. I don't know, man. But you're actually modifying G at each step. It's something like this. It's a little strange. Yeah, it's definitely odd. I don't know if this works. Like, we'll try it. We'll see what happens. And we're going to say it's the beginning. And we're actually going to erase that iterator. Say string. So this is the next stop. We're going to say current.pushback s. We're going to call f with all of these things, which are num stops plus 1. The next one is which stop s. And then pop it off the back. And g of which stop insert of s. So you erase this, then you reset it back to that spot, which is super strange. And then, yeah, that's kind of it actually. Erase, push it, recurse, pop, and then push this back in. And right, increment the number of stops. It's something like this. Like, it's actually kind of really simple. We just do if current is less than ret, then ret equals current. Lexicographically, that should work, I think. I think that's it. I think it's like a really simple recursive routine here. I just don't, it doesn't feel right, you know? It doesn't quite feel right. Why am I using a multiset? I don't know. Do I really need to use it? Oh, the reason I'm using a multiset is so I can erase it as if it were a set, but it's a multiset, so it's got more. See if it compiles. Okay, it's wrong. Nice. So they don't really need num stops either. Can just do current.size. Let's go to n plus 1. Oh. Also, or a ret.empty. Something like that. Oh, there we go, it works. Oh, wow. It works. What? Compiles and everything. I think the last one at the bottom doesn't make sense. I think this one's not supposed to work, to do anything. What was this test case that we failed on? Do we just go for it now? I think we do. Huh. That's that simple, huh? Yeah, I thought it would be that simple. I thought so. The reason why we want to use a multi-set and a set is that a regular set could cause issues because you could have a ticket, you have like multiples of the same ticket basically. And then if you did that with the problem with a vector is that you have to find and remove the vector, which can be kind of expensive. And then also, so you don't want to use a set, but you don't want to use a set because if you only have one, so if you have multiples of a ticket, then you have issues where you remove that ticket, but you want to reuse it later. So you use a multi-set here for those things. Does this work? Do we have problems? Time limit exceeded. It's depressing. Brother, really? You gotta be kidding me. It's TLEs. I thought. No, really? What? How are you supposed to handle? Oh no. AXA as AUA. To AXA again. No, to where does AUA go? To JFK. Back to ES. Back to a new. To AXA again. To ADL. Oh, look at all these tickets, man. What? Oh no. Oh, please no. Say it ain't so. It took me so long just to get to here. Just to get to 48 minutes just to get to a simple DFS that works. But alas, we need something more efficient. How are you supposed to do something more efficient than that exactly? Because you know as well as I do. You know as well as I do that, I mean, the main problem we have is that we don't know what all these cycles are, or these paths are, and brother. Yeah, so the problem with this is that you can have potentially a large branching factor, you would call that, for your search algorithm. And yeah, this does loop through. Oh, you know what, actually, I think it might be the problem. I think it may be, no, it can't be. No, this shouldn't be an issue. Yeah, I mean, this is kind of like all of the permutations. This is sort of. This is in some sense. I think it's exponential. The amount of time this would take. This takes, which is expensive. Could argue something like, well, maybe it shouldn't be exponential. I don't know. Maybe we need to go learn more about Eulerian paths to figure this out. Think about this. Constructing trails and circuits. Fleury's algorithm. Herholtz's algorithm. Oh. Overall algorithm takes linear time. Oh wow. Implemented with a queue. Only possible to get stuck when the queue represents a closed tour. One should rotate the queue, remove an element from the head, and add it to the tail until unstuck. Continue until all edges are counted for. All stakes linear times, number of rotations performed are never larger than E. So, okay. This is an interesting question, interesting problem. However, it's definitely stuff that I haven't really studied very much. So it's kind of like I'm in like uncharted territory a little bit here. The 5-room puzzle. Oh, excuse me. Special cases, interesting. P-complete problems. Polynomial, okay. Oh. Huh. Counting Eulerian circuits in undirected graphs is much more difficult. Hashtag P-complete. Sharp P or number P. Problems in this class are defined by having the following two properties. Sharp P. Those problems can be defined as counting the number of accepting paths of polynomial time, non-deterministic Turing machine. Sharp P hard, meaning that every other problem in Sharp P is a Turing reduction. 2-hit counting reduction. Parsimonious reductions, a more specific type of reduction preserves the exact number of solutions are used. Polynomial time algorithm solving a Sharp P complete problem if it existed would solve the P versus NP problem by applying that P and NP are equal. No such algorithm is known, nor is a proof known that such an algorithm does not exist. So this is Sharp P. Okay. Never mind. Oh. This is what I learned to be NP. Sharp P. What is this? Is this different from NP? Probabilistic algorithms. Oh. Easy problems with hard counting versions. Some Sharp P complete problems correspond to easy polynomial time problems. Satisfiability of a Boolean formula DNF is easy. Satisfiable if and only if it contains a satisfying conjunction. Counting the number of satisfying assignments. Yeah, see that's the problem I'm looking for. Sharp P versus yeah. Oh boy. Getting sick here. The number of circuits can be calculated using digraphs, the best theorem. Number of circuits in a digraph is the product of a certain degree, excuse me, of gas, man, of gas. Certain degree of factorials in the number of rooted arborescences, computed as a determinant by the matrix tree theorem, giving a polynomial time algorithm. Best theorem is first stated in this form in a note added in proof to the Ardennes, Ehrenfest, and de Bruijn paper. Original proof was bijective and generalized to de Bruijn sequences as a variation on an earlier result by Smith and Toot. Counting the number of Eulerian circuits on undirected graphs is much more difficult. Undirected. Really, undirected is more difficult. It's bound to be sharp P. Digraphs. Directed graphs. Oh, we're looking at directed graphs. Arborescence. Directed graph in which for vertex u called the root and any other vertex v there's exactly one directed path from u to v. Arborescence is thus the directed graph form of a rooted tree, understood here as an undirected graph. An arborescence, or basically a rooted tree. That's what I thought it might be. It's a fun word. Arborescence is a directed rooted tree in which all edges point away from the root. A number of other equivalent characterizations exist. Every arborescence is a directed acyclic graph, but not every DAG is an arborescence. Really? Is that true? I don't think that's, is that true? Wait, I don't know if that's true. Really? I thought every DAG is an arborescence because if you point back to the root, then you have a cycle, right? Oh, that's weird. Arborescence can equivalently be defined as a rooted digraph in which the path from the root to any other vertex is unique. That's interesting. An out tree. Large number of synonyms for arborescence in graph theory. Directed rooted tree, out arborescence, out tree, even branching being used. The same concept, rooted tree itself, has been defined by some authors as a directed graph. So anyway, okay. The number can be calculated using the best theorem. Number of circuits in a digraph is the product of certain degree factorials in the number of rooted arborescences. Can be computed as a determinant by the matrix tree theorem, giving a polynomial time algorithm. Okay, because I think we need to loop through all of these. Like, that's the problem we're having here. Different methods for finding cycles is more efficient than Fleury's algorithm. I'm gonna need to look at both of these, I guess. By using a data structure as a double linked list, maintain a set of unused edges, incident each vertex, maintain a list of vertices, current tour that have unused edges, and to maintain the tour itself. Individual operations of the algorithm, finding unused edges, exiting each vertex, finding a new starting vertex for a tour, and connecting two tours. Share vertex may be performed in constant time each, so the overall algorithm takes linear time. Did this get, I got a lot of downvotes, yeah. I'm wondering if it's because it's like you have to know sort of specific algorithm, Herholtz's algorithm for Eulerian paths in order to really solve this efficiently. Like a simple DFS really should suffice, I guess, but I don't know, whatever. This algorithm may also be implemented with a queue, because it is only possible to get stuck when the queue represents a closed tour. One should rotate the queue, move an element from the head and add it to the tail until unstuck, continue on until all edges are accounted for. It takes linear time as the number of rotations is never larger than E. So we're actually going to implement Herholtz's algorithm for this one. I think I kind of just want to go to bed, just give it a rest. So we got kind of wrecked by this problem. Not only is it a graph search problem, it's an Eulerian cycle. It's not cycle. It's an Eulerian path problem, which obviously our depth first search is not sufficient, right? They're looking for basically an algorithm to handle this better, mo better. to use Herholtz's algorithm, which is unfamiliar to me, and quite frankly, I don't think I would have come up with that on the spot just for this question. I guess I guess it's not too hard to figure out, but it's definitely, it'll be interesting, I guess, to do this. So I think what I'm going to do is just end it here and say thank you for watching. Excuse me, and go ahead and end the stream here. So thank you for watching, and say have a good night. Talk to you soon. Thanks again. Oh, and take a look at this again tomorrow. Make it part 1 for this, and the part 2 will be actually implementing that algorithm that's described in the Wikipedia, and maybe think about it, try to kind of understand why it works. Something like that, I don't think I would be able to think up on the spot. I would have to know that algorithm beforehand, which it's something that's kind of wonky or funky about a lot of these questions and sites like this, is that there's often some kind of maths involved that you're really not familiar with, and that'll give you sort of the most efficient answer, and you really wouldn't be expected to know these things. Like you wouldn't know. These are not things that are normally covered. I mean, Hamiltonian and Eulerian paths and cycles are covered in basic graph theory. However, you wouldn't cover like the Herholzer algorithm, for instance. Probably not. So I don't want to say it's not fair, but there's this kind of like, you're going to know a whole lot of stuff you really probably don't even need to know, really, if you kind of go through all these problems. However, I guess it's good to do this stuff, to learn these things, to kind of get more familiar with all these different algorithms. I don't know how I feel about it all. It feels maybe like I'm spending way too much time on this stuff. When I come across things like this, it's like, how much do you really need to know? Like what is the point? Why am I doing this? I think the main reason is that I had set out to do something like this a long time ago, solve all the problems on the site, and I kind of never quite got there. And I also, I've had a lot of rejections from different companies and different, I guess, opportunities in life for various reasons. And one of them is like algorithm questions. I think, although it really seems like only like the really large tech companies care about these algorithms. It seems like other companies really just care if you seem to have an idea of what they're trying to do and can help them. Anyway, so yeah, thank you again for watching. Talk to you soon. Have a good night.